So last time we talked about the forward solution and the basic linear minimum norm inverse solution. And so what I want to talk about today is kind of a grab bag of topics. So first, talk a little bit more about the noise normalization I talked about at the end of the minimum norm inverse as a way of sort of viewing the solution that's a little more informative, more sort of stat-like. And then also some recommendations about like what kind of data to include. Like should we use more sensors? Should we always include MEG and EEG? Is EEG better than MEG or vice versa? So that's the first topic. And the second topic, I'll talk about what if we have some MRI data in addition to EEG and or MEG data? Can we sort of combine them somehow? Because EEG MEG have very good temporal resolution, fMRI has better spatial resolution. Is there some way to sort of combine those? And there is, but with caveats. So that's number two. Number three, we'll talk about the surface normal constraint, sort of problems with it, sort of positive aspects of it, problems with it. That was the original motivation for FreeSurfer, because FreeSurfer was written in the days before functional MRI. And then finally, we'll talk about using the covariance of the sensor data over time, spatiotemporal covariance, as a way of sort of helping out with some of the minimum norm problems, and then also, problems with that. So it's sort of a grab bag of more advanced topics on the inverse. They're all about the inverse problem of trying to decide where sources are given some data from outside the head. Okay, so starting off with the point spread function. So generally when you say point spread function, what do you mean? Well, you just sort of mean you got a point, and then what does it turn? How does it spread out? And so in the current case, you can, so if you have some source somewhere, so say there's a source here, particular orientation of a source, what the point spread function is let's assume that we have a source there. We can just do this in a modeling study. So we calculate a forward solution, and then we invert that forward solution to try to figure out where it came from. So basically, we start with a point source, and then we calculate the forward solution. So that's the A matrix, that's the forward solution. And so from that point source, we get some kind of distribution over all the sensors, and then we just invert it immediately without doing anything else. So this is, so we basically take a point source, a point source is a vector, multiply it by the forward solution A. That gives us some data, and then we just take a data vector, then we take that data vector and multiply it by the inverse solution matrix, and we get another vector, which is a vector of where we thought that data that came from a single point went to. And what will happen? Well, it's going to smear it out into a big blob like that. So all of those, it will say all of those things could have given rise to that point. And there's another very similar, so what is that? That's the sensitivity of surrounding points to 1. So sensitivity of surrounding points to a single source. And you could also, something that's very closely related would be the crosstalk. So and that would be basically how much the surrounding points affect you. So let me get that out of there. So how much do the surrounding points affect your estimate? And so in that case, there's you. And then the question is like, how much contamination do you get from the surrounding points? So this one is the sensitivity of surrounding points to one point, that point. And this guy is, how much do surrounding points affect one point, same point. So that same point there. Okay, so what I'm summarizing some data. You can go into the readings to look at it. It's data from Liu and Dale. Liu, Dale, 2002. So basically, just doing modeling studies, you can essentially determine, what is the best way of, if we include, say, EEG and MEG data, or use more sensors, how does that sort of affect our point spread function in a positive way by making it smaller, for instance, so that we would have less blurring. And you can also see what is the effect of doing that noise normalization on the point spread function. And so the last time we said that one of the problems is that deeper sources have have bigger point spread function. So if you take a superficial source, calculate the forward solution, invert it immediately, you get a smaller amount of point spread than if you take a deeper source. And with a deeper source, you calculate the forward solution and invert it, you get this huge smear all over the place. And that was, and it's also going to displace sources to the surface, because you can get away with a smaller norm with a solution that has superficial sources, all because of the inverse square property of the forward solution. So one of the reasons for doing the noise normalization is that it basically equalizes noise norm equalizes the point spread function. Point spread function, superficial deep. It actually sort of damages the point spread function for superficial sources, but makes it equivalent, makes the point spread function for deeper sources smaller. So it makes them, sort of equalizes them. And that's there's kind of more mathematical rationale for, why to do that noise normalization. So from doing these kinds of studies, just modeling studies, you reconstruct somebody's brain, calculate the forward solution, using, say, boundary element method, calculate the inverse using the standard minimum norm, and then maybe do some noise normalization on it. And then you can say, what kind of recommendations should we make for collecting data? And so our sort of, recommendations. So the first one is not surprising. More sensors, better. So if you have more EEG or more MEG, that's going to be better. That's not surprising. That should be kind of obvious. But another interesting one is that EEG is better than MEG. EEG alone. EEG alone better than MEG alone. So why is that? MEG alone. So, there's a lot of, competition between EEG and MEG. Sometimes, MEG has been posed as an alternative to EEG, that, a more expensive alternative, whereas EEG has often been said, like, well, we're just as good as you, but we're cheaper. The bottom line is it's actually better to use, both of them. But why is EEG alone better than MEG alone? And the reason has to do with the forward solution. It's something I didn't mention last time, but let me just go over it quickly. So if we have MEG, so let's put MEG up here. If we have a tangential source in MEG, so here's a brain, and say we've got a tangential source like that. Like, for instance, something in the central sulcus, like, say, the hand area. That's about the hand area in the central sulcus. So if you do your, you've got some field going into the board there, and then sort of coming out of the board down below. So this is what's the amplitude of the magnetic field looks like. So it's going to be minus here and plus here. So it's coming out down here. So you get a nice big signal from a nice big MEG signal from a tangential source. Now, if you were in an infinite conductor, you would get a signal from a radial source. But it turns out in a spherical conductor, or something that's close to a spherical conductor, you don't get anything from a radial source. So in an infinite conductor, you should be able to see something if the brain filled the universe. But the bottom line here is that this gives 0. So if you have a radial dipole in MEG, you just don't see any MEG signal from it. And because of that, if you just sum across the brain, EEG is going to be better. So what happens in EEG for those two cases? Both of those cases in EEG give you a signal. So if you have a signal like this, if you have a dipole like that, the forward solution of that dipole, you're going to see some sort of current coming out of the head here, and then some current going into the head here, if this is your zero point. So a tangential dipole gives you a signal, and then of course a radial dipole will give you a signal as well. And so because of the forward solution would sort of look something like that. So this is our EEG case. So that's one downside of MEG alone, is that you can't see radial dipoles. Now, if they're off by like 10, 20 degrees, that's probably enough. If they're not perfectly, radial, then maybe off by 20 degrees, you can start to see them. But there's definitely some holes in the top of every gyrus where, you would get quite a big signal from an EEG recording. So that's actually, cheaper is actually overall better than more expensive MEG. And the reason for that, is because, radial dipole, MEG, spherical conductor is 0. But the other thing you can do is, like, what about mixing different kinds of data? And so it turns out the biggest gain, because these kind of signals are basically kind of orthogonal to each other, perpendicular to each other, the biggest gain, from adding small number sensors, other type. So you gain a lot by adding some sensors of the other type. So the thing with MEG is MEG detectors are sort of arranged into this device, and there's a lot of them, and like there might be 300 individual squids in MEG, and so it's kind of just no problem collecting a lot of those. But it turns out even adding just 30 EEG electrodes, it would be nice to have 256 EEG electrodes, but that's like a giant pain to put on. Make sure that each one of the electrodes has a low impedance, has a good contact with your scalp. With 256 electrodes, it's a lot of scratching. So basically, even a small number of EEG electrodes, helps. And so you might have, say, 300 MEG just built into the detector, but even just 30 EEG is a big help. Now, the problem, like I said, is it's a pain in the butt to also collect EEG when you're collecting MEG, because you've got to put an electrode cap on. It has to be a non-magnetic electrode cap. You've got to 3D localize where all the electrodes are in order to figure out where they are in relation to the MEG, in relation to the head. So it's extra work, but in general, it's worth it if you're trying to localize. And then finally, the fourth thing is that there's a problem, which is that the EEG, MEG forward solution scaling is not straightforward. And so what does that mean? That means, like, for a given source, when we calculate our forward solution, there's enough unknowns in it that we can be off between the effect of a single source on EEG and the effect of a single source on MEG. So, in other words, there's just this sort of unknown number in there. Like, for a given amount of source down here, source J down here, so like in these two cases, what is the ratio between the EEG and the MEG solution? A little bit unknown. So what does that do? That can cause more blurring, so error causes some blurring. So that's another issue. Now there's ways to fix this. You could insert a dipole and then actually, like for instance, if somebody has an electrode in their head, and then you could turn on some current through that electrode, and then measure the EEG and measure the MEG induced by that little current dipole. How would you do that? You would put a little electrode into the head like this with a twisted pair, and then just have a little exposed part like that, where the wire is exposed. And so then what you could do is basically induce a little dipole, a little current dipole. It's all twisted until you get to the little dipole part, and then measure the EEG and MEG, and then you would have a correct number. Now, obviously, you're not going to do that with the average undergraduate subject, so that's another thing to keep in mind. So that was the point spread function and recommendations. Now, do people do this? Very rarely. They should do it more. It's not that much harder to collect, both EEG and MEG. But people, in general, rarely do this, even though it would greatly improve your localization. It's kind of like, the downfall of humanity is just slightly easier. So, okay, so let's now turn to fMRI constrained inverse. So, one of the big advantages of fMRI is you have a very good spatial resolution, but the temporal resolution is pretty bad because you're just looking at this exhaust of, of the oxygenated blood it's delayed. Now, I talked in one of the 8 a.m. lectures about the possibility of, recording something more like membrane potential with fMRI, this so-called Diana technique. And, if people can get that to work in humans, that potentially could give you much better temporal resolution, but nobody's gotten it to work so far in humans. So fMRI constrained. There we go. Okay, so is there some way we can just combine high spatial resolution fMRI data with high temporal resolution MEG, EEG data? Now, the answer is you're never going to be able to do the following. Just by combining EEG and MEG, end up with something that is MEG, EEG temporal resolution, and fMRI spatial resolution. But you can make some advances, and so let's just look at some of the problems with it. So the inverse solution matrix is this W matrix that you multiply your data by in order to get all the sources. When we wrote it out last time, it had all these other matrices in it, and there was the covariance matrix of the sources, the assumed covariance matrix of the sources, the transpose of the forward solution, and then times the forward solution again, times the covariance of the sources again, times the transpose of the forward solution again, plus the covariance matrix of the noise, which is something we could measure, and then that whole thing inverted. So that's how you get that W matrix. But one of the matrices in here was this R matrix, and what that R matrix is it's a big square matrix, of sensors by sensors. Sources, by sources. And what is it? It's just down the diagonal, it has the variance of each source. And then, off diagonal, it's a symmetric matrix of the covariance, of source I, J. So how do all the possible pairs of sources, how correlated are they? So we said that what we did initially is we just stuck in 0. We just assumed that nobody's correlated with anybody, and we put small equal numbers down the diagonal. So this is the variance down the diagonal. So that's source 1 times source 1, and then source 2 times source 2. So and so that's the variance going that way. So that's this guy. It's also over here. So instead, what we could do is we could put in some variance that corresponds to data that we recorded from fMRI in a similar experiment. Now, you can't do fMRI and EEG, MEG at the same time. People have actually tried this. They've tried to sort of combine some kind of MEG detector with a fMRI magnet that you can turn on and off, believe it or not. It's not a very high field one, but like an electromagnet. You could turn an electromagnet on, collect some data, turn it off, wait until the field sort of settles down, and then collect some MEG data. It's pretty hard to do that. So basically you would just do some MEG recording, EEG recording, and then do some. You can do EEG recording and fMRI at the same time, but MEG is a lot harder. So what could you use this for? Well, imagine we've got, we've done some experiment, and say we've got some, we've done an fMRI experiment, and say we've got some sort of MT plus data, and maybe some sort of superior parietal data, and maybe dorsolateral prefrontal data, something like that. So this is, that's like something you typically get. So here's some stuff, up in parietal, and here's some, dorsal, lateral, prefrontal cortex. Okay, so now the problem is, so let's go over here and say, say this was the dorsolateral prefrontal sources, and just turn them up a little, turn up the variance. Don't turn everybody else down to completely zero, we'll see. And then, say MT was down here, so turn these guys up, and then say, turn parietal up over here. So now what to do with the ones that didn't have any fMRI data at them? And so one thing we could do is we could just turn them to zero. We could say like, I expect that there should be no variance for these other spots. So that would be a bad thing. So no fMRI. So plan 1 is 0. That's a bad thing to do. So why is that? Well, say there was, say there was the frontal eye fields here, and for whatever reason you didn't collect enough repetitions of your fMRI data, or there's some slight difference between the event-related thing you were doing for the EEG data and the way you were doing the fMRI experiment, and let's say you just didn't pick up that data didn't reach significance in the frontal eye fields. Now, if this was the frontal eye field focus and you turned it to 0, so if we turn these guys to 0, completely to 0, what would happen then? If your EEG, MEG data picked up some signal from there. So say your EEG, MEG data picked up, it picked up a signal, a signal from MT, it picked up a signal from parietal, it picked up a signal from dorsolateral prefrontal cortex, and it picked up a little signal from the frontal eye fields. So now we've got a problem in our inverse that we have to somehow explain that data, which actually occurred in the MEG and EEG, with these dipoles. And so what's going to happen is you're going to get some funky set of these dipoles turning themselves way up to generate a field at a distance that explains that data. So then there's plan B, so small. So if you turn all the fMRI points, instead of turning them to 0, just turn them to small, then this problem won't occur. But what will it do? So what it will do is it will essentially cause the data, this EEG MEG data that came from the frontal eye fields, to essentially get smeared out into very small values over a large area. So it will gracefully disappear the frontal eye field data by just essentially causing a whole bunch of, it will be because all the other sources, including the frontal eye field, but also including, say, like here and here, are going to be turned down to low variance, not 0 variance. Then that will be allowed to absorb this real signal here. So at first you might say, wow, that's not good. There was an actual real signal and we killed it. And yes, that's what we did. We gracefully killed it in a way that it didn't damage our estimate of these other large signals. So this just gives you some idea of like the sort of the various trade-offs you have when you're trying to combine this data. Now what's the good news? Well, for sources that we can see both in fMRI and EEG, MEG, we now have a time course. We now have a real time course. So the good news, good news is that we can get a millisecond time course for sources visible in both. So the bad news is mismatch gets dissipated dissipated gracefully. That's what we like to say, gracefully. So we dissipate anything that doesn't show up in both gracefully without sort of damaging the ones that we actually were able to localize. But there's another point. Say we have in the dorsolateral prefrontal cortex, say there was in the fMRI, say there was actually 2 spots that we can clearly distinguish in the fMRI. So we could see there were two spots there. And now let's say that those 2 spots are within the point spread function for the inverse problem, and which they would be if they were about that spacing, if they're like a centimeter apart. If they have the same orientation, dipole orientation, and they're a centimeter apart, they're not going to be distinguishable. So can we somehow sort of increase the fundamental spatial resolution of the MEG and the EEG? And the answer is no. There's no way that we could reliably assign our MEG, EEG data to one or another of those sources if they're within the point spread function of the fundamental point spread function of the EEG, MEG. So you can never really truly just magically get fMRI spatial resolution with EEG, MEG temporal resolution. What you can do is you can basically get the time course for a reasonably well isolated site that's it's not too small. It's not too small, and actually sort of see the time course. So the bad news is never can get all the way to fMRI spatial plus MEG, EEG temporal. But what can we do? And I just mentioned this last time. What we can do is, we can divide the brain up into like 20 or 30, 1 to 2 centimeter patches like this. We can distinguish things like in this ballpark. We can tell the frontal eye fields apart from dorsolateral frontal cortex from orbitofrontal. It's kind of hard to tell sort of operculum from anterior temporal because those are very close to each other. But in any case, what we can do is we can get a millisecond picture of this, 1 to 2 centimeter patches as the information moves around. So like, you can see information moving to, MT, maybe going to dorsolateral prefrontal, maybe coming back to parietal, or, going back to, eventually going back to V1. So that's a good thing. So that, that gives us some dynamic picture of where stuff is going to in the brain. People should do more of this. They've done relatively little of this kind of thing. Now, all these, like I said, last year, all these problems are there with your standard EEG temporal components. They're just kind of swept under the rug. When you're doing, like, if you're just looking at the N1, how does the N1, vary with stimulus condition? All these problems are all there. It's not like they weren't there. They're all there affecting, like, that temporal component. But this, using static spatial components, is sort of a more sensible way of approaching this problem at looking how information is flowing around in the brain. So it's not perfect, You're never going to get exactly, fMRI spatial resolution with EEG, MEG temporal resolution, but by combining them, putting those source variance estimates from your fMRI data into your inverse, it's possible to, to actually start to see something that's closer to fMRI spatial resolution with EEG, MEG temporal resolution. Okay, so now let's talk about the surface normal constraint, the original reason for making FreeSurfer. So what's the good news? So the good news is that, why were we trying to use the surface normal constraint? Well, it turns out that so here if we make a nice big brain here, so there's some skull over it, and let's make a couple sulci here. So here's a gyrus, another gyrus. Okay. So what's the good news? So the good news is if we've got a source here versus a source here, so we'll call that A and B. There's A, there's B. So those sources are very easily distinguishable in MEG, EEG. So we're back to surface normal constraint on EEG, MEG inverse. So those are very easily distinguishable. And why is that? It's because when you rotate a dipole, it massively changes the scalp distribution of both the EEG and the MEG. Like in MEG, suddenly just rotating this dipole that much would suddenly, make a much bigger forward solution for B than for A. So you can easily distinguish things that are well under a centimeter apart from each other, just a couple millimeters apart along the cortex. So that's the good news. Good news. A and B easily distinguishable. And that was really the original motivation for using the surface normal constraint, because knowing that the forward solution changes a whole lot when you rotate a dipole. But the bad news is, unfortunately, that if you have something over here, down a little bit further, or something over here, or something over here, so we'll call those, C, D, and E. Those turn out to be really hard to tell apart. So the bad news is, same orientation, same orientation, difficult. And the reason is because that doesn't change the forward solution. We don't change the rotation of the dipole. The forward solution just changes quite subtly over the surface. And given the point spread function, you basically can't distinguish those. But now let's just sort of look in more detail at what's going on there. There's a weird point spread function for surface normal constrained. Which I already sort of mentioned. That's what I mentioned. So we can easily tell apart points that are close to each other, but C, D, E hard. So these are much further apart from each other as you move along the cortical surface. And so if you flatten that out, so if I flatten out that cortical surface, what are you going to see? Well, you're going to see the possibility of some negative current here. So that's going, some positive current here. That's going from the, deep in the cortex to the superficial in the cortex. And then you're going to see kind of nada from down here. And then you're going to see some negative current here. It's the same orientation of the dipole, but in this case, that same oriented dipole infers that you had a negative dipole going from the cortical surface down into the deeper layers. And now we're back from the deeper layers back up to the cortical surface. And so what are you going to see when you flatten it out? Well, it's going to be kind of gnarly. You're going to see like some positive current here, and then you're going to see nothing down here, and then you're going to see some negative current, and then you're going to see nothing up there, and then you're going to see some positive current right here. So you'll see, plus, minus, plus. And so when he first started doing this, we said like, the sign isn't that important. Just square it and take the power. Isn't that what you really want to know? You want to know sort of approximately where the activity really is. But the ERP people were not happy with that because sign is everything, like the N1 versus the P1. Solution, take power. That was not acceptable. Just take the absolute value. That would still end up with these little sort of stripes in between, in the sort of deeper part of the sulci and the superficial parts of the sulci. So typically what people have done to solve this problem instead is just solve onto dipole triples. So at each chunk of the cortex like this, instead of just putting one dipole perpendicular to the cortex, just put 3 dipoles like this, 3 possible unit dipoles. So that triples your number of dipoles. So if you had like 10,000, now you got 30,000. That's okay. What's another couple thousand when you're already off by, you already got like 10 times as many unknowns as knowns. So basically if you just use these, solve onto dipole triples. So they're still located at a particular point in the cortex, so you're still constraining your solution to be in the cortex, but you're not using the actual orientation directly. So, but still, I can't. What if you really wanted to go crazy? So, just look up this paper by Donald Hagler, who is one of my former postdocs, and what he's done is done visual mapping with fMRI, and then used very localized spatial stimuli so that you make a very sparse set of activations, and then do a whole bunch of different sparse locations in the visual field, and then make a big giant inverse that sort of solves for them all at the same time, using the surface normal constraint. So this is, if you want to just see like the absolute state of the art, so this is, use surface normal, sparse stimuli, and big giant inverse. So just make it a big inverse that includes all these separate stimulus types, and in order to really get down to individual cortical areas. That's really sort of going beyond the pale, but I put that in the readings. You can take a look at that in the readings. So the bottom line is, surface normal constraint has this weird point spread function, with these stripes in it, and so people typically instead just solve onto these, dipole triples. Dipole triple at, each cortical location. To get around that problem. And what that will do is that will just kind of fill in this whole thing right here, like that. The whole thing will get filled in. You won't get those stripes anymore. Okay. So any questions about that? So that was point spread function, fMRI constrained inverse, how to sort of carefully combine the two kinds of information, and then how to deal with the surface normal. Relatively hard to use unless you just go completely full metal jacket, like Don Hagler. Okay, so last but not least, let's talk about using the sensor data covariance. Now, what have we been talking about, last week with the forward and the inverse? You notice there was no time. There was no time in the forward solution. And so what we're doing is we just get a single temporal snapshot of data, and then we calculate an inverse solution. And then we get the next temporal snapshot of data and calculate the inverse. So we don't have to recalculate it. We just multiply the inverse solution times that next snapshot, that vector of data from the next temporal snapshot. And so there's no time. It doesn't take any advantage of time. It's just doing single time points. The inverse is just applied to single time point data. But is there some way we could sort of take advantage of the fact that we're recording a whole bunch of time points from the same thing, and different things are happening during different time points? So those matrices that we talked about the R matrix. That was the spatial covariance. It's really spatial temporal covariance, right? Because it's spatial temporal, because it's measured over time, like we would do in an fMRI experiment. Spatial temporal covariance of sources. And then we had the C matrix, which was the spatial temporal covariance of the sensor noise. And that's something we could also measure. We could just, try to put a gelatin head and just see what the correlation between the noise and the different EEG electrodes or different MEG electrodes is. But there's another matrix D, which is one after C, and this is the spatial temporal covariance of sensor data plus noise. Plus noise. And so let's just sort of get some intuition why it's why we could get something out of that, something more out of that than we could just get out of our basic instantaneous minimum norm inverse. And so this was originally called music, multiple something, I can't remember what it is, what it stands for. And that was the original paper by Mosher and Leahy, Patrick Leahy, 1992. And then there's a paper by Dale and Serino in the 1993 to sort of apply that to the cortical surface. But this it's not a new idea. It's sometimes called beam forming. If you want to read the literature, beam forming, that's a very similar idea. And it's been heavily used in astronomy for speckle interferometry. So when you look through a telescope at a point source, a really dim point source, there's all this atmospheric noise happening constantly, and it's very difficult to sort of pick up something coming from that point source. But if you look at a spatial covariance of what's going on, what you can see is that every once in a while you'll see a nice signal from that point source that comes from that, which has a spread due to a point source, and then you can basically localize a point source in an extremely noisy environment. So it's all based on the sensor covariance. So what's the intuition? So the intuition is, let's assume we had so we'll give two different situations. So it can help with this minimum norm problem, but it can also help with the problem of ghost sources, where there's a single source that looks like two other sources, because if you look at the forward solution, there's all different ways in which it's underdetermined. So say we have some signal at a single point in time that look like that. So what could have caused that? Well, it's possible it was caused by two sources like this that were on at the same time, but it's also possible that it was caused by a slightly deeper source, like that. We'll call this guy sort of a ghost source. It could have been caused, so if these guys were always on at the same time, or at the particular moment of data that you're running through the inverse, they were on at the same time, then basically you're not going to be able to tell those, you're not going to be able to tell those two superficial sources apart from a single, slightly stronger, deeper source. So now if you record data over time, however, maybe we could do better. And so if we record data over time, so we could have two different situations. So one situation would be we see sensor data that looks like one source, and then maybe we see data that looks like both at the same time, and then we see one that looks like this. So here maybe both sources were on. Maybe now at this time point only one was on, at this time point only one was on. So this is time 1, time 2, time 3. And if we saw that data, then we would say, oh, it's probably superficial sources. But alternatively, if we saw data that just at all the time points looked like two on at the same time, well, then we're sort of screwed, because it could be either one. Could either be a deep source or the superficial source. So time 1, time 2. But you can see that by examining the covariance, which means the spatial patterns, the covariance here, if you did covariance on this whole thing, what you would see is sometimes you had that spatial covariance, sometimes you had this spatial covariance, sometimes you had this spatial covariance. And so it gives you a way of basically disambiguating some things that would be ambiguous at a single time point. So that's the temporal aspect that we're taking advantage of, which we were not taking advantage of in our original minimum norm inverse, which was just an instantaneous calculation. But so that's like for ghost dipoles. It can help with that. But it can also help with deep dipoles. So one of the problems, and this is how Anders Dale and I originally were trying to pitch this. So if you have a situation where at a single time point, so here's your single time point, you had an actual deep source. So say you had an actual deep source at this single time point right here. What's going to happen? Well, the minimum norm is going to say, well, I can get away with a smaller norm by just displacing that to the surface because of the inverse square forward solution. My total norm is going to be smaller than using that deeper source. And so what will happen is if you see a signal, that looks like that, that's consistent with a deeper source, in general, you're in the minimum norm is going to say, well, I'm going to displace it to the surface. So how could the spatiotemporal covariance of the sources help with that? Well, similar to this previous case, if you record several time points and you see something, that looks like a superficial source, and maybe or something that looks like two superficial sources. So if you actually see something like that, then it probably is a bunch of superficial sources. So these are two different possible data that might have arisen. So if you see something like this, that indicates that it probably was, a small superficial source here and then a small superficial source like that. But on the other hand, if you never see those little bumps in your spatial pattern of the covariance, which we'll sort of unpack in just a bit, then it actually is a deep source. And so what would that look like? That would look like, so remember this is, these are different time points, like time 1, time 2, time 3. So if instead you actually had across time 1, time 2, time 3, just something that looked like that, and you never had a localized spatial pattern in your covariance that looked like that, then it's not the superficial sources. So in that case, you can say, I know for sure it actually was a deep source. And so this is so these are two possible situations that might have occurred. So it might have actually been a bunch of superficial sources, or it might have just been a deep source. And so this is one way of solving the displacement to the surface problem. You just basically look at the spatial covariance of your data and see, is there anything like that in it? If not, you say, I know it's not a superficial source. It has to be a deep one. And so that's one way of sort of fixing the minimum norm. And so let's just go over a little bit of the, I won't go over all the math, but I'll just go over the basic plan of how we do the math. So to do this, what we have to do is somehow calculate the spatiotemporal covariance of the data plus noise. And so what is that? That is basically just for an instant in time, look at all the possible pairs of sensors and just multiply. That's what correlation means. It just means multiply. Just multiply them, each pair times, one of each pair times the other of each pair. And then just do the same thing over time for each time point. Sum the whole mess up, and then you get a covariance matrix. So if you go into the paper and look at the equation for D, so what is D, that spatial temporal covariance matrix? It's the expectation of the data times the data vector times the data vector transposed, and expectation means over a bunch of examples of that. I won't unpack that any further, but we've got noise in there, so the noise is in there, so here's the standard deviation of the noise squared times the identity matrix, and then we're now going to look at the sum across all the possible pairs of sensors. And what are we looking at? We're looking at the correlation between, I and J, and then multiplied, going through the forward solution. So we have to go through the forward solution in order to get up into the sensor space instead of the source space. And that guy's transposed. Okay, so what is that approximately equal to? So that's approximately equal to the thing that I just said in words when I was erasing, which is multiply each pair of sensor data points times themselves, and then just average that over time. That's what the sensor spatiotemporal covariance matrix is. And so how would you write that out? We would write it out as, here's a vector of data, and here's another vector of data for time point 2 out to time point n, and we just multiply that times the transpose of that. And so I'll sort of I'll unpack that down below. So what does that mean? So each one of these x's is a vector of data, and that one is transposed. So let's put it off. Let's put it down here. So if you assume that a vector like x, a vector is a column vector, then if you take the transpose of a column vector to turn it into a row vector, so what does that look like? If you transpose the vector and multiply it like that, the rules of matrix multiplication give you a dot product. So if we transpose x and then multiply it by x, what do we get? We get a number, single number, because it's just, this one times that plus this times that plus this times that. So, and that's the dot product. So we started off with a vector, and we demoted it to a number. So, that's the dot product. But alternatively, what we could do is do it the other way around. So we could multiply, so that this was like this case. we could do it the other way around. Take a column vector and multiply it by a row vector. And if you do that, you get a matrix. So we actually, in this case, we've promoted those vectors to a matrix. Equals, a correlation matrix. So what happens with that? You basically just correlate each individually. You end up with an n by n matrix. That's the correlation of each entry in that vector with each other entry in the vector, and then also the variance would be the correlation of each vector with itself. So we haven't got to this yet. So what is this? This is a bunch of vectors. So if you think of vectors as basically column vectors, this is a bunch of column vectors, also known as a matrix. So what happens if you start off with what we actually have there, which I left out the divide by the number of entries. So there's the n right there. So if you divide by the number of entries, and then we essentially multiply a whole series of vectors, also known as a matrix, times a whole series of vectors that is transposed, we still get a matrix. And this one is, this one is our spatiotemporal covariance matrix. Spatial temp covar matrix. So in that case, we're actually multiplying like a matrix times a matrix. So there's a typo in the paper. I forgot to put the typesetters forgot to put the T in there, but you can add that T in there. Okay, so all this means is just take a time point, multiply all the different sensors times each other, and multiply including the sensors times themselves. Do it again and again and again. Divide by the total number of time points you have. And you don't have to do this across all time. It's possible you could do, say you got a bunch of time points like this, you could have a sliding window, sort of like calculate it across this time, if this is time going this direction, and then do it again. So you could get like D1, and then you could get D2, etc. So now that we've got that, what do we do with it? So now we have to somehow categorize the spatial patterns, because this D, what is this D? It's kind of it's a summary of all the spatial patterns that have occurred. So that's the way I think of it, as a summary of all spatial patterns of sensor data, across our stim. So now we have to somehow kind of break it up into different spatial patterns in order to see whether or not the spatial patterns that occurred were, say, those little superficial ones like we saw with the minimum norm displaced to the surface, or were they all deeper ones? And so one way of breaking up, sort of factoring a matrix, covariance matrix like that, is to do something like principal components, to break it down into its orthogonal components, meaning spatial patterns that aren't correlated with each other. Now these aren't necessarily spatial patterns coming from one dipole. It's just an arbitrary way of factoring the matrix into a set of spatial patterns that are all uncorrelated with each other. And so what does that look like? So we take this D matrix, which is kind of a record of all the spatial patterns that have occurred during our stimulus, and we factor it into 3 matrices, or actually 2 matrices. So here's our 3 matrices. And so if we draw those matrices out, what are they? They're basically a bunch of eigenvectors. Those are uncorrelated, meaning orthogonal to each other, perpendicular to each other, spatial patterns, so spatial patterns that are not correlated with each other at all, and then some eigenvalues in the middle that tell us what is the strength of each of those spatial patterns, because they have to all add together back into our final, covariance matrix. So this is so here's like U1. So that's the first eigenvector. There's U2. So what is, so these are eigenvectors. So they're all perpendicular to each other. So each one of those columns is perpendicular to each other, meaning uncorrelated with each other, a spatial pattern that has no correlation with another spatial pattern. So that's our U matrix. It's a square matrix. And then it's multiplied by that capital lambda matrix here, which is our eigenvectors, our eigenvalues. And the eigenvalues are basically how strong each of those patterns are. And then it's all 0. So that's an identity matrix with just the, these are the eigenvalues. It's all linear because we're just adding up. We're just essentially taking this matrix and factoring it into a bunch of different spatial patterns, each of which has a weight. That's really, you got to think of this very concretely. So these just weight how each of these different spatial patterns got added together to generate our final covariance matrix. And then, since it's a covariance matrix that's squared, we've got to sort of multiply it by. So this guy is the set of eigenvectors here, and this guy is just eigenvalues, and this is just the eigenvectors again transposed. So that basically sort of factors things into our. Here are the spatial patterns that occurred during this stimulus, and the eigenvalues say how strong was each of these spatial patterns, and each of these spatial patterns are perpendicular to each other, orthogonal to each other, uncorrelated with each other. It means the same thing. So they aren't the right spatial patterns. They're not sort of a way of finding dipoles. They're just a way of sort of categorizing what occurred during the experiment in a compact, weighted way. And then what you can do is you can try to scan through your dipoles in order to eliminate ones that couldn't have occurred. So how does this work? So let's just take a dipole here. Take some dipole here. And now let's say, so these eigenvalues down here are small. These are ordered eigenvalues. They're ordered by size. So you go and look at the small eigenvalues. So small eigenvalues, and those are spatial patterns that didn't occur very much in our covariance matrix. And so what we can say is, let's calculate the forward solution of this guy. So here's the forward solution of this one. So calculate the forward. So that's multiplied by the A matrix. Calculate the forward solution, and then forward solution will generate a spatial pattern. And then we can say, does that spatial pattern look like these small eigenvalues? So the question is, does this spatial pattern look like eigenvectors with small eigenvalues? And if yes, get rid of it, okay? If yes, turn off. You could just say turn down. So you can go through the math in the paper of how to sort of just stamp it down without completely shutting it off. And so then what do? You just go to the next dipole and the next dipole, and then eventually you try dipoles up here on the surface. And that's how you can get rid of a lot of the displacement to the surface problem, because these guys will generate a forward solution that looks like that, and that will be way down in the small eigenvalues. And so since it's in the small eigenvalues, we know there probably wasn't a source there. So that's a method. You can call it beamforming or speckle interferometry, or spatial covariance, or factoring into the noise space, the signal space and the noise space. But basically what it is just a way of using your data over time to rule out some of the dipoles. And so like these superficial dipoles never generated a spatial pattern that appeared in our catalog of spatial patterns, and so we tossed that one. So this seems like great. Like what's the problem? Well, there's a specific problem. So good news. It solves minimum norm problem. But the bad news, it makes the assumption that dipoles are not perfectly correlated. Assumes sources not strongly correlated. Now, strongly correlated means like over 0.9, like really strongly correlated. So let's examine what happens if they are strongly correlated. So for instance, let's make an auditory click. So if you make an auditory click, both auditory cortices will both come up at the same time with extremely high correlation, like 0.99 correlation. You'll see two signals come up in the two auditory cortices. Now when we do our scanning process, what's going to happen? Well, what are the big eigenvalues going to be? The first big eigenvalues are going to be two blobs from the left and the right auditory cortex. When we scan through with single dipoles, what's going to happen? Well, none of them are going to look like that because every single dipole is a single blob, not a pair of blobs. And so if your sources are extremely well correlated, then this is going to fail. So you could fix that by, instead of scanning one dipole at a time, you could scan all possible combinations of two dipoles at a time and look at the forward solutions of all possible dipoles of two at a time to sort of fix this problem. But you can see it's not perfect. It's not perfect. But this is one way of trying to sort of exploit the data over time, rather than just confining ourselves to just a single instantaneous inverse problem. And this is, and if you read in the literature, you'll find like 20 or 50 or 100 different versions of the same thing, of trying to use the sensor covariance over time to try to help solve your inverse problem. Like other problems, you can see, it fails sometimes if you have like extremely strongly correlated sources, but on a good day, it will completely solve the minimum norm problem, and discover that you really had a deep source, not a whole bunch of little superficial sources. Okay, so any questions about this? You can sort of see why people shy away from some of the localization, because it's kind of much more hairy than the sort of standard fMRI, but you get great stuff out of it. You actually sort of see where the activity is is going, going across time. Okay, well, I guess that wraps it up.